Hi everyone, I'm Aviv Tamar from Technion, and today I'll talk about learning to plan and planning to learn. So this talk is about sequential decision making, has many applications in robotics, computer systems, operation research, and many others. And the two main paradigms for sequential decision making are either planning or reinforcement learning. You plan by trial and error. Both of these paradigms have been explored intensively and by itself. But if you look at humans, for example, it's clear that we have both trial and error learning, and we also learn from raw sensory inputs when we're young at least. But it's also clear that we plan, at least when we make once in a lifetime decisions. We probably do this also every day when we try to avoid trial and error. And we're pretty good at generalizing. So the question that I'm asking is whether the combination of planning and trial and error learning could help us design algorithms that are better at generalization. In this talk today, I'm going to talk about learning to plan, where we're going to ask whether neural networks can actually learn planning policies. And we'll talk about a new RL formulation that we call sub-goal trees for this task. In the second part, we're going to do the opposite. We're going to ask how can we plan to learn as quickly as possible in a new task through Bayesian reinforcement learning. Let me start with the first part. Can neural network policies plan? So what do we mean when we say neural networks that plan? We think about an agent that takes its input, some observation of the problem, does some neural network computations on it, and outputs an action. And hopefully these actions are good in the sense that they solve the problem. How can you train such a network? So in reinforcement learning, for example, we do trial and error and try to maximize or minimize the expected costs on our training domains. In imitation learning, we might have an expert that tells us what is the best action to take in a particular set of observations, and we just try to imitate that. The question is, how do we generalize to a task that we haven't seen before? Or equivalently, what happens when the task changes from what we've seen in our data? And to answer this, we took what is probably the simplest setting you can think of. This is called a grid world. So this red agent that needs to navigate through these obstacles towards the goal. And we took, what was at the time, a deep CovNet, similar to one that was used to solve Atari games. And we trained it on procedurally generated instances of these grid worlds. And the hope was that it would learn how to kind of navigate safely towards the goal. For humans, it requires just a glance to figure it out. But what we found is that it's very difficult to get these neural networks to solve a test task. So they do perfect on the training, but they kind of memorize the training and they don't generalize well. And we tried many tricks, nothing really worked well. When we tried to figure it out, our inspiration was inverse optimal control, or inverse RL, where we thought that what should happen in this neural network is it needs to map the observation to kind of a model, plan in that model, and then output an action. And then when the observation would change, it would map it to a different model, and then the planning would kind of adapt itself, and then it would generalize. The question is how to design such neural networks and how to train them using backprop. So let me tell you one idea. Here's one explicit planning algorithm. It's called value iteration. So think about this grid world, and let's say you want to calculate the shortest path towards the goal. This can be done iteratively by going over all of the states, and for each state, you calculate or you minimize the cost to one of the neighbors plus what you currently estimate is the distance from that neighbor towards the goal, and you repeat that iteratively. And we know that this would converge to the shortest path, shortest distance towards the goal. Now, if you have stochastic transitions, well, you just need to take the expectation over the neighbors. Once we looked at this, we saw that this is actually very similar to the computation that goes on in a convolutional neural network. Think of a convolution takes each pixel and that's a linear computation with its neighbors, and there's some max pooling steps after that. And these are actually the same computations, but organized a little bit differently. So if you believe that you can backwarp through a convnet, you can actually backwarp through value iteration algorithm. With this idea in mind, we designed what we call a value iteration network, which has this differentiable value iteration planning algorithm as a part of the network itself. So the neural network maps from our observation to some kind of planning computation, and the output of that planning computation, the value function, is being used to output an action. The point here is that once we're training, what we're learning is how to map an observation to the relevant planning computation that outputs an action, the one that explains our data the best. This generalizes much better. Here's an example on our test map. You see in red the trajectory predicted, in blue the shortest path, and we can actually visualize, inspect it, and see what it learned. So it learned to give high cost to hitting obstacles, low cost around the free space, and high reward to getting to the goal. And this induces, during planning, a short path to the goal. So we never taught it this reward. This is what it learned to pick up just from observing data of shortest paths. This idea is actually more general. So you can think of different planning, differentiable planning algorithms that you can backward through and embed in type of neural networks. So several follow-up applications included navigation in a first-person view and driving in a crowd. And we backward through model predictive control, and other groups used different planning algorithms to use in different problems. The main takeaway is that this is kind of an inductive bias. If you know something about the relevant planning problem, you get much better generalization. So now to understand that neural networks have some fundamental capability of planning, we can ask how to use that. And one idea is to make standard planning algorithms faster. So if you think about standard planning, a planner takes as input some problem description, does some computation, and outputs the relevant plan or actions. But if all of your problems are similar, think about this robot in a warehouse, that it navigates the same warehouse every day, but the task may be different, or maybe there are minor variations. We should exploit knowledge from solving previous tasks. The way we can do this is we can replace this whole planning algorithm with a deep neural network that takes some visualization of the problem as input and outputs an action. We can train it on solved instances for a long time, and it would be very slow. But then once we see a new problem, we just need to run a forward pass of the network to get a solution. So just to convince you that this can solve non-trivial problems, here's on right work on learning continuous motion planning. And you see that it learned to navigate kind of very tight corridors. It's a neural network that outputs the next action in the plan. And on the left is Sokoban. This red agent needs to navigate or push this purple objects to the green goals. Because it can only push them, it becomes a non-trivial planning problem. And what you see here is a neural network that was trained just using imitation learning, and it's being evaluated on maps that it hasn't seen before. And you see that it at least seems that it's doing some kind of planning about 30 steps into the future. It's just to show that there is some promise in training neural networks to perform planning computations. You should ask, however, how well does this do? All right, so I can give you some numbers. In this case, on Sokoban, we get to 87% success rate on 2 objects. But what does that mean? Maybe a more informative question is the following. If we picked up some structure of how a good plan looks like in these problems, we should be able to use it as a heuristic and to improve standard planners. So we did that. And here's a graph that shows some results. On the x-axis is the plan length, so shorter is better. This is the plan quality. And on the y-axis is the number of states explored during the search. So lower means faster. The green on the top, the green dot on the top is the llama planner, which we use to generate our data. It's an optimal planner. So it, by definition, it generates the shortest plans on average. On the blue, however, is A star with a neural network heuristic. And note that it's almost as optimal as llama, almost as good, but several orders of magnitude faster. So this really shows that we managed to pick up some structure of how a good solution to this problem looks like and use it effectively. All right. The next part of the talk is a more recent work that we call subgoal trees, which came about when we start to think a bit more deeply about what it means to learn to plan. So remember that the essence of planning algorithms is that they are multi-goal. They should be able to solve any task that you give them. We want a neural network to replace the planner, and we can train it using reinforcement learning, but RL by definition is a single goal problem. So we have one cost function in an MDP. So how can we bridge this gap? Well, what we've seen so far is that we can just add the goal as a particular part of the state. So in these maps, we saw both the current position and the goal position. And then you can just run some RL algorithms on it. So this can work, but the question is whether this is the optimal thing to do. So let me give you some motivation why it shouldn't be. So let's think about this deterministic problems of just shortest path on a graph. We know that running value iteration, which is the equivalent of a single goal RL here, or Bellman 4 algorithm, has a worst case running time of n cubed. Now, if you want to run Bellman 4 for every possible goal, that would require n to the power of 4 iterations. This is what effectively RL does when we just add the goal as another part of the state. And this is what many approaches in the literature currently do. But we know that for the all-pair shortest problem, we have much faster algorithms. So for example, Floyd-Warshall is n cubed. That means that there is some structure to exploit here that we are missing when we're just adding the goal as a part of the observation. What we wanted to do is derive reinforcement learning algorithms from a different first principle, not the standard Bellman equation, but the all-pair shortest path problem. And I'll show you that we can actually do this. We can get some theory, and we can also have some algorithms that work with deep neural networks. Just to give some formalism, we consider all-pair shortest path on a graph. So we have a directed and weighted graph with no negative cost, and we assume that the graph is fully connected. So if you have an unconnected edge, just assign a very high cost there. What we want is to find the shortest cost trajectory between each pair of nodes in the graph. So to introduce our way of doing this, I'll first describe what is the standard kind of Bellman equation approach of thinking about a trajectory. So the standard way of computing the next state and trajectory is asking, given the current state and the goal, what is the next state? And then once you move to that state, you ask what is the next state and so on until you complete the trajectory. We're going to ask something different. Given a state and a goal, we're going to ask what is the middle state between them. And then we break up the problem into two different independent problems, and we're going to compute the sub-goal in between them. And then we get 4 different problems and so on until we figure out all the sub-goals, and then we make up the whole trajectory. So you can write down a dynamic programming algorithm using this idea that we call sub-goal trees. And the way to do it is define the value function v sub k of s and s prime as the length of the shortest path between s and s prime in 2 to the power of k steps or less. And this value function obeys a fundamental equation that's shown here in purple, which effectively reads like the shortest distance between two nodes in, say, 16 steps or less is equivalent to the sum of shortest distances that are 8 steps or less that go through a shared subgoal, S sub m. And using this equation, you can kind of build up the shortest path between all of the nodes iteratively. If you think about it, you only need to run log n iterations of this algorithm because the value is to the power of k steps or less. And each iteration, you need to do n cubed calculations. You go over all the states, all the goals, and all the sub-goals. So you get n cubed log n complexity. The important thing here is that this is better than n to the power 4, which means that we exploited something of the structure of the all pair shortest path problem. Now we would want to use this new principle to design RL algorithms. And the first thing we need to do is handle approximations. We want to handle large state spaces. And the question is whether subgroup trees handle approximation better than just standard RL. So to answer this, we need to look at how error propagates. I'll give you kind of the gist of the idea. The full theory is in our paper. So the gist of it is that if you think of a subgroup tree, in the lowest level of the tree, you have some error, let's say epsilon in your value. And once you move up a step, you add two different value functions, you get at most 2 epsilon error on the trajectories of length 2. And then for trajectories of length 4, you get 4 epsilon, and so on, until you make up the whole trajectory and you get n epsilon. How does it work for the standard Bellman type RL? Well, at each iteration, you get another epsilon. And that sums up to n epsilon as well. So at least it seems that both subgoal trees and standard RL has the kind of the same error propagation. But after you compute the value function, what you need to do is you need to compute a trajectory from it. And here is where the subgoal trees shine. And the reason is that once you go on and try to use the value function to compute the trajectory, on the first iteration of subgoal trees, the first prediction would have the largest error, the n epsilon. That's the first subgoal. But then the other subgoals would have half of that error, and then a quarter of that, and so on. And if you sum up all the errors, what you get is n log n. On the other hand, standard Bellman type approach would have the highest error on the first step, n epsilon again, but then on the second step it would be n minus 1 and n minus 2 and so on. And if you sum up all these errors, they are linear, so you get n squared error accumulation. So this means that subgoal trees have effectively less drift, much more stable. You can design reinforcement learning algorithms using the subgoal tree principle. We have several of them in our paper. Here's an example with an equivalent of the fitted queue algorithm that we call fitted subgoal trees. And this is applied to continuous kind of a maze here. And you see on the right the learned value functions, and you see that the yellow is the unreachable parts. And you see that as you increase k in the value, the area in the maze that is unreachable decreases until for k equals 6 here, you can reach any part of the maze towards the goal. Comparing to the standard RL algorithms, subgoal trees here had a much better performance. That's explained by our theory. We saw that the standard fitted queue algorithms kind of had a very large drift, and they learned to just kind of wander around and avoid obstacles. But subgoal trees learned to actually reach the goal. Here's a different algorithm using subgoal trees. This is a policy gradient approach. We applied it to a 7-bluff robot arm that does motion planning around an obstacle. And it does a linear motion between the subgoals. And here's an example of the subgoals that it predicted. And you see that a linear motion between them results in a feasible trajectory. And again, we measured it on various different starting and goal positions, and our algorithm generalized much better than a baseline that was not built on subgoal trees. So to summarize, we propose a new framework for RL that has a very different first principle, which is the all pairs shortest path problem. We proved that it's more efficient in the deterministic setting, and this is the basis for many new algorithms and theory. So far we've talked about how to learn to plan, basically how to teach a network to solve a planning computation. The next part, we're going to ask a different question, and we're going to plan how to learn. We're going to plan how to solve a new task more efficiently. And to give you the motivation, think about this very simple particle that needs to navigate to a goal. How would reinforcement learning solve it? Well, it would first kind of randomize, explore randomly until it stumbles upon the goal, and that will give it some signal to kind of zone in on the correct trajectory and reach it quickly. This is very slow. We'd want to make it faster, so we need some kind of information. What if I told you that the sub-goals, that the goals could be somewhere on this half circle? The way I'm telling you this is I'm letting you train different RL agents, each one with a different goal position. And then you get all this data from your training, and you can use it to infer where the goals could be. So one thing you can do in this case is that you can use the data to infer the goal distribution and learn how to reach a particular goal. And then you just sample a possible goal, see if the goal it's there or not. If it is, you're done. You go there again. If not, just choose another point that you haven't visited before. This is called Thompson sampling, and it's quite easy to learn from the data that we have, which consists of agents that navigate to particular goals. And this is what has been done before. But once you think about it, this is not the optimal way to explore here. A much more efficient search would be to actually search along the half circle until we find the goal, and then go directly towards it. The problem is, well, this is Bayes optimal. This is the optimal thing we can do here. In a sense, I'll explain exactly what this means. But this is very different. At least the trajectory that searches along the half circle is very different than what we saw in our data. So how can we use this offline data to learn such efficient exploration behavior? This is what we set out to solve. And before I tell you the solution, let me convince you that this is one of the most important problems we need to solve right now. The reason is that offline data is the safest way to collect data in many situations, for example, robotics or healthcare. We don't want agents that just randomly try out many different things. And this doesn't really have to be limited to particular tasks or goals, but we can think of different tasks as the type of the robot, or the patient profile in a healthcare application, or the customer profile in an online shopping app. We want to suggest the customer the particular advertisements that have the highest chance of informing what the customer wants and directing towards a buy. But we need to explore this very quickly, otherwise we'll just risk losing the customer. So there are many, many applications of potential applications of this idea, and let's talk about how we can actually do this. So first, there are two types of exploration in RL. The first one is the more popular one, which doesn't assume any information about the problem. And the best thing you can do in this setting is kind of don't waste time on non-interesting states, things that don't have reward or you have already visited before. And for this, you can derive kind of worst case bounds. There's also the Bayesian RL approach, where you have some prior about the possible tasks that you can experience. And in this case, you can actually plan your exploration to obtain the maximum information or reward. So here, there is a well-defined optimal exploration. The way this is formalized is we have a prior distribution over the possible MDP parameters, and we try to maximize the expected reward with respect to these parameters as well. So the agent doesn't know which MDP it's in. It has to kind of figure that out to maximize the expected reward. This is essentially a POMDP, but its solution, which is a history-dependent policy, is the optimal exploration trade-off. This is great. This means that we can actually explore optimally in a new task. But, well, POMDPs are intractable. So you might get discouraged. But the good news is that recent advances in deep meta-reinforcement learning actually made very nice progress in solving POMDPs using deep reinforcement learning, and this is what we use here as well. So the particular algorithm that we built our work on is called very bad, very nice algorithm for Zingraf et al. And the way very bad works is it maintains some belief about the particular MDP that the agent is in. And it's a neural network that estimates its belief using a variational training of a recurrent neural network. The output at each time step is a posterior probability over the MDP that's represented by means and covariances of a Gaussian. These means and covariances actually encode the posterior distribution or the belief and can be input to another policy neural network that can actually use them to plan ahead how to explore effectively. So Veribet is an online algorithm. What we ask is whether it can work offline, where we only have data of training histories of RL agents. There is an inherent problem here that we call MDP ambiguity. And here's the thing. Let's say we had two trajectories in our data, one with reward at the left circle and one in the right blue circle. How can you tell from these two trajectories that there are actually two different MDPs with two rewards at each position, or just one MDP with rewards at both positions? If you can't tell that from the data, there's no way that you can effectively infer which MDP you're in just from this data alone. This is a difficult problem, and it's unique to this offline Bayesian RL setting. So we formulated it a bit more carefully, and the way to formulate it was that, okay, well, let's say there are different different MDPs in some that we have in our training set that are part of some hypothesis set. And we use some policies to collect data on these MDPs, and we have data distributions. Identifiability means that there is no single MDP in the hypothesis set that can, and two policies that can induce two different data distributions. That means that there is no MDP where here with rewards, so for example, here, think of an MDP with rewards at both locations. There is two different policies that can explain both of the trajectories that we saw. So one way to control or to guarantee identifiability is to control the hypothesis set. If all the MDPs only have one reward, then we don't have a problem. But if our hypothesis, if we learn using neural networks, it's not really feasible to control this. So we have a different approach. So an identifying state is a state where with different rewards transition between the two different MDPs. And we identify that a sufficient condition for identifiability is that every two different MDPs visit in our data some identifying state. Basically here, we need the MDP with the left reward, we need trajectories both from the reward and to visit the blue area and see that there is no reward there. This is basically what this means. And if we can guarantee that, if we can satisfy that, this works for any hypothesis. This is what we prove in the paper. So this means that easy problems for offline meta-RL are problems where the solution or a feasible approach to the solution visits many identifying states. For example, the popular half-cheetah domain where you need to learn to run in a particular speed, well, most likely that you'll visit the identifying states where you see the reward gives you, identifies what speed you're running in. So you will know, according to the reward at every state, if you need to run faster or slower. But this sparse reward setting is much more difficult because unless you visit the reward and see that there is no reward in anywhere else, then you don't know which MDP you're in. So how can you collect identifiable data? We propose two simple strategies. The first is called a replay policy. Instead of collecting data from a single agent from a single MDP, you use the policies from all the other agents. And that we show that this guarantees identifiability. Another approach is that if the MDP is only differing the reward functions, you can apply this replay in hindsight. Just take a trajectory and relabel all the rewards there from rewards from a different MDP. And this, again, it can guarantee identifiability, and this can be applied to any offline data, as long as you know the rewards and you're training it. So our algorithm that we call BOREL, for Bayesian offline reinforcement learning, takes as input the data, simply applies this policy replay or reward relabeling, then passes this data, modified data, to train a VAE as in very bad, and then continues with a standard very bad approach. Here are some results. We trained it on different tasks, discrete and continuous and with image inputs. And in all of them, we saw that we significantly outperform Thompson sampling baseline. And this is because we're actually training a Bayes optimal policy. We also saw that in tasks where the reward was sparse, where MDP ambiguity is a concern, the reward relabeling solutions work much, much better. Let me see you. So what we see here is a result on the first two episodes, which is where the most significance of efficient exploration takes place. Here's an example similar to the particle environment in the beginning. This is a ant robot that needs to learn to navigate on this half circle and search for the goal in the first episode. And then in the second episode, after it found it, it goes directly to the goal. So it learns just by observing data of tasks where the goal was, of RL agents trained where the goal was at particular locations on this half circle. It never had specific instructions of searching around the half circle. So to conclude, this is the first offline deep Bayesian RL algorithm. And the key to making it work is solving the MDP ambiguity problem. We solve it through data collection. It's interesting to see whether exploration could be also used to solve this problem. And we think that this is a step towards deployed agents that can actually explore efficiently in a new environment. Thank you very much. And I'd also like to thank all my collaborators in these projects.